Okay, so today I'm going to be solving this physics problem right here that is technically it's under the category of simple harmonic motion. However, it definitely involves a couple other concepts from mechanics, Newtonian mechanics. So let me just read it real quick. So we have a smaller disk of radius r, so this disk right here, and mass m is attached rigidly to the face of a second larger disk of radius capital R and mass capital M, as shown in the figure. The center of the small disk is located at the edge of the large disk. Okay. The large disk is mounted at its center on a frictionless axle, and then the assembly is rotated through a small angle theta from its equilibrium position and released. And then we're supposed to show that the speed of the center of mass show that the speed of the center of the small disk as it passes through equilibrium is that expression. Okay, that was a mouthful, but so we're supposed to show the speed of the center of the smaller circle here, or the smaller disk here. So we could solve this a couple different ways. One is by using Newton's second law, which might be a little complicated, but a slightly easier way to do it is just to think of it in terms of energy, conservation of energy. So I'm just going to, I'm actually going to draw another picture. So let's see. I'm going to draw the larger disk here. So this is the larger disk. And then I'm going to draw it such that we pull it at an angle. So here's the smaller disk. Here's the smaller disk. And we pull it and release it from rest. So I'll make that a little straighter. So we pull it at an angle theta and release it from rest. So let's think about some energy. First of all, I'm just going to write down the conservation of energy equation. Write it over here. So we'll say that the initial kinetic energy plus the initial potential energy is equal to the final kinetic plus the final potential. Okay, so we're saying that we pull it at an angle theta and release it from rest from this point, which means that there's no initial kinetic energy. I guess I should define where my reference point is for the gravitational potential energy. So let me go like this. Let me say that, so when the disk swings down, it's going to reach its equilibrium right here, and that's where we want to find the speed. So let me call its lowest point right here. I'll call that y equal to 0. I'll move this down a little bit. So this is going to be y equal to 0, which means that this distance right here, I'll call it h, that is its distance above the reference point, so that would be the height for its gravitational potential energy. So I guess before finding out what h equals in terms of, the radii and the angle, let me first write, m, g, h. And keep in mind that the smaller disk has a mass of little m, and the bigger the bigger radius has a mass of capital M, but the bigger disk is not moving relative to the y equal to 0 point. It's just the smaller mass, so that's why we just have little m, gh. Okay, and then there's not going to be any final potential energy at the equilibrium point right here, but there will be kinetic energy, but it's going to be rotational kinetic energy because this disk is rotating about this center point, as it says in the problem. It says mounted at its center on a frictionless axle. Okay, so instead of 1/2 mv squared, it's going to be 1/2 I, whatever the moment of inertia is, and then omega squared, angular velocity. Okay, so now we need to find out what h is and I is. So let's look at h first. So let me first draw this, make this right triangle right here. So there's a right triangle, right? Okay, there's the right angle. And I guess I should put some labels. So this distance right here is r, capital R, if we look at the figure. I guess for completeness, I could say that this little distance here is lowercase r. And then this distance would also be r right here. So for h, we want r, which is this whole distance here, minus this little bit right here, which will give us this bit, which is h. So this piece right here is going to be, well, it's r, hypotenuse of that triangle, and then times the cosine of theta, because that side is adjacent to the angle. So we have an r cos theta here, which means that h is, well, it's r minus r cos theta, or r times 1 minus cos theta. Okay, so that's h in terms of r and theta. Now let's talk about I. I'm just going to move this over a little bit. So the moment of inertia. Well, moment of inertia is going to involve both disks, because we're pulling both disks at an angle of theta, right? It's because the smaller disk is attached to the bigger disk. So the moment of inertia, I'll say, moment of inertia for the big mass, capital M, is, well, so it just says, let's see, where does it say? A second larger disk of radius capital R and mass capital M, and we're rotating about its center right here. So without going into a derivation, you could just find this on any table of, moment of inertias. The moment of inertia of a disk, a solid disk, rotating about its center of mass is 1/2 times the mass times the radius squared, like that. Okay, that one's not so bad. Now let's talk about the moment of inertia for the little mass. Okay, so for this case, we have this little mass that is rotating about this center point, but not rotating about its own center of mass. So we're going to have to use the parallel axis theorem, which I'll write, I guess, real quick up here. So the moment of inertia about a parallel axis, I'll say P for parallel axis, is, well, we say the moment of inertia about its center of mass, so whatever that is, plus the total mass, I'll just say little m, but this is the total mass of whatever object we're talking about, times, I'll say d squared, where d is the distance between axes. Okay, so if we go back to our picture, so the moment of inertia of the little mass, the little circle, the little disk, is, well, we're going to have to use this parallel axis theorem. So the moment of inertia of it about its own center of mass, again, is a solid disk. So that's 1/2 little m, because we're talking about the little sphere, and then its radius, which is a little r squared. Okay, but then we have to add to it the total mass of that thing, which is just little m again, times the distance between axes. So that would be the distance between this point and this point, because this is the axis that it's actually rotating about, and this is the axis of its center of mass if it was rotating about its center of mass. And from this picture, we can see that that distance is just the radius of the bigger disk. So this would just be r squared, capital R squared, like that. Okay, so that means that the moment of inertia total of this system, of the small disk and the big disk, is just the sum of that. So that'd be 1/2 capital M capital R squared plus 1/2 little m little r squared, and then plus little m capital R squared. Kind of long, but that's it. Okay. Now, let us rewrite the potential, or rewrite the energy equation right here in terms of all these given variables. So we have mg times h, where h is this right here. So that's just capital R times 1 minus cos theta. And that's equal to 1/2 times this moment of inertia, which I'm just going to copy and paste because it's kind of a long expression. Okay. And then this omega squared. Well, if the smaller disk, if we just focus on the center point of the disk, which is what we're trying to eventually get, is an expression for the speed of its center of mass, then we can relate, or not the speed of its center of mass, but yeah, I guess the speed of its center of mass, the speed of its center point. In this case, its center point is its center of mass, so yeah. So in this case, we can use the following relation that, well, the velocity of the center of mass of a rigid body is the radius times the angular velocity, which means that the angular velocity is the velocity of the center of mass divided by the radius, which means that omega squared from here can be rewritten as the velocity of its center of mass squared divided by the radius squared, capital R squared. Okay. And I guess I should note that it's not the little r squared, because this thing, this little disk right here, when it oscillates, when it's rotating like this, and its radius of rotation, I guess if you want to say it like that, is this capital R. So that would be relating its angular velocity about this point, like this, and its, tangential velocity of the center of mass. Okay, so now we're trying to solve for this, the velocity of the center of mass. That is what we're trying to show right here. And we have all, given variables. We have r's and m's and thetas. Now it's just a matter of doing some algebra to show that it equals that. So one thing that I'm going to do is take this and just make it into one fraction, because just be easier to deal with. So the first two terms are already over 2, so we can say this is capital M R squared plus little m little r squared over 2, over 2 plus m r squared. Okay, and then one more step, this is over 1, then to get a common denominator, we just cross multiply to get the numerators. So we'll do we'll do this times this plus this times this over 2. So that's capital MR squared plus MR squared, just times 1 doesn't change anything. And then plus 2 times little m capital R squared. And then it's just over 2. So that is the not simplify, but it's the moment of inertia just in one fraction, okay? And then it's multiplied by a half. So I'm going to say, so from the left side, we have mgr, capital R, times 1 minus cos theta, and that equals this fraction right here, but over 4 because the 2 is multiplied to become a 4. And then we still are being multiplied by this velocity of the center mass squared divided by the radius squared. Okay, so now what I'm going to do is I'm going to basically divide both sides by this big fraction, which means just multiply by the reciprocal. So I'm going to flip the equation and get that the velocity of the center of mass squared divided by the radius squared is equal to, so I'm going to flip the fraction, this fraction, and write that. So that's 4 over capital M R squared, capital R squared, plus little m little r squared, plus 2 little m capital R squared. And then that's multiplied by still mgr times 1 minus cos theta. Okay, and then I'm just going to multiply both sides by r squared to get the velocity of the center mass squared isolated. And instead of rewriting, I'm just going to go like this. I'm going to do a little rearranging like this. So this 4 can go over there. This can move on to the numerator like this. Get rid of this sign. And then, like if I multiply it by r squared here, those cancel. But then I have to multiply by r squared here, which makes this r get a cubed by it. So that's me multiplying by r squared on both sides without having to rewrite it. Okay, so if we look back up here to this, we're trying to show this, and it looks kind of like it. We have a 1 minus cosine. We have a 1 minus cosine. We got m's and r's floating around, but it's not quite the same. Also, this 1/2 right there comes from, just taking the square root of this. So that's fine. Okay, so now it's just a little bit of algebraic manipulation to get it look exactly like what they want. So if we notice on the top, there's only an r and a g on the top. Here we have a 4 mgr cubed. I guess the 4, when we take the square root, the 4 can become a 2 actually, and that's where this 2 comes from right here. Oops, I circled that in white. This 2 comes from right there. So that's fine, we don't need to worry about that. So let's see. So they have 1 capital R on the top. So you know what? Let's just multiply. I'll extend this. We'll extend this fraction bar. Let's just multiply this by 1 over r squared. And I know that's a little weird, but if we do that, then we only get a single r on top. But of course, if we do that, we have to do it down here as well. Okay, so we get 4 mg and then just r because this r squared cancels with that. And then we still have a 1 minus cosine theta. And now on the bottom, we have to distribute that. So I guess, I could go like this. Divide by r squared, divide by r squared, divide by r squared. And that actually we get some nice simplifications. That goes away, and that goes away. So we just get capital M plus, I'm going to write it like this, M times R over capital R squared, and then plus just 2M. Okay, so let's see, we have a 4mgr on the top right here, and when it says show that equals this, they don't have an M right here, no M. So let's just kind of do what we just did, and let's just multiply, I already do it in red, multiply this by 1 over M, because then that M would cancel with that M. But then we'd have to multiply this by 1 over M as well, which I guess I could just write it as this divided by M, this divided by M, and this divided by M, which we also get some nice simplifications. That cancels with that, and that cancels with that. So what we're left with is that the velocity of the center of mass squared is 4 gr times 1 minus cos theta divided by m divided, or capital M divided by little m, plus little r over big R squared plus 2. So that looks really close. All that's left is to take the square root, which I'm just going to write as 1/2 because that's how they have it. So now the velocity of the center of mass is, well, so when we take a square root like this, we can take the square root of the numerator and then the denominator, so we could do this. Furthermore, on the numerator, we could do this. All that goes to say is that we can just do the square root of 4, which is 2, and plop it out here. And then instead of writing a square root, like I said, I'm going to do 1/2. So we have, I think they write it as RG, so I'm just going to flip that. So we have RG times 1 minus cos theta divided by capital M divided by little m plus little r divided by big R squared plus 2 to the 1/2. And I believe, let's just move this down. And that looks pretty good. So here we have shown that the velocity of the center of mass equals that complicated expression. Okay. So now the next problem, the next question says, show that the period of this motion is another long expression. Okay, so for that, we are going to have to do a little more calculation. First of all, let me just write that. So the period, right, of any oscillation of a simple harmonic oscillator is 2 pi divided by omega, right, where omega is the angular frequency, which comes from, so if you set up Newton's second law and you get that, I think the most classic example is with a box on a spring. If you get that the acceleration equals negative some constant times x, then this is a simple harmonic motion. And you could even write acceleration as the second derivative of position with respect to time equals negative some constant times x. So anytime you have the second derivative of a function equaling the function itself and a negative sign and then some constant, that means that the solution is x equals some constant a times cosine. You could use sine, but I'm going to use cosine of omega t. I'll say plus phi. So this is the solution where omega is a constant, which is the same constant as this. Phi is the phase shift. We don't really need to worry too much about that. But either way, that's the solution. So if we can set up this equation, I guess I should say that omega is given by the square root of this constant, whatever you get here, which depends on the situation. All that goes to say is if we can find an expression for omega, then we can do, 2 pi over omega, and that gives us the period, which is what we're trying to find. So we're going to have to set up Newton's second law. But we're actually going to use Newton's second law of rotation because if you look at the problem, we have something that's rotating, not translating. So Newton's second law of rotation. So Newton's second law of rotation says that the sum of all the torques on an object is equal to the moment of inertia times the angular acceleration. Well, the moment of inertia we already found from above. Alpha is just the second derivative of the angle with respect to time. So if we can find an expression for the net torque on this system, and it involves a constant and then a negative sign and then theta, then we can define omega and get the period. So let's go back up to the picture up here that I drew up first. So when thinking about torque, we need to pick an axis of rotation, which kind of already picked it here, but this is a very convenient one because if you remember, torque as a vector is defined to be the cross product of the position vector crossed with the force vector. Okay, so if we pretend this circle that I just drew is the big disk, then gravity acts on its center of mass like this, capital MG. But the position vector, by the way, this position vector extends from the axis of rotation to the point where the force is applied. So to the force. So if we think about it, this is the axis of rotation. What's the distance from this point to the axis of rotation? Well, it's 0, which means that no torque by gravity on the big mass. So we only need to think about torques by the little mass. So let me erase this real quick. So it might be easier to think of it like this. The magnitude of the torque is, well, just RF, the magnitudes of those vectors, times the sine of the angle between them. So let me draw another little picture here. So let's go like this. This is the big mass. This is the big disk. There's the axis of rotation. We have the little disk right here. I'm not going to draw it as a disk, but the center of mass is right here. So gravity for this disk acts like this, little m g, and the distance connecting the axis of rotation to the point where the force is applied is this distance right here, which is just the radius of that big disk. And then the angle between them is, well, if we continue this line of force, like that, I know it's not that straight, but imagine it's straight. So the angle would be here, which I just labeled theta because, I guess I should have done this first. This angle we define to be theta from up here and from the problem right here, which means that this angle is also theta by some simple geometry. You can kind of see it, if this line goes down, this line goes here, this line continues, and this line goes straight down. These two lines are parallel, so this angle, those two angles are the same. You can also think of it as making a right triangle here, and then making this right angle, but that's beside the point. All that goes to say is that this is the angle between them, theta. So the magnitude of the torque is the position vector r, which is in this case the radius, times the force, which is mg, times the sine of the angle between them, which is just theta. So that is the expression for the torque on the little mass, or the little disk. So let's go back down to here and say, so the net torque, that's the only torque that we have. So what did I say it was? It was mg for the force, r for the distance, sine theta. And then I should note that there is a negative sign, and that's because the torque is always pulling the object, the little mass, towards its equilibrium. So if you imagine right now, the torque is pulling it this way, but if the object swung and was over here, oops, that's a bad drawing. If it swung and was over here, the torque would be pulling back this way. So it's always towards equilibrium. So that would be a restoring force. So we throw the negative in there to indicate that it's a restoring force, or a restoring torque in this case. So we have negative mgr sine theta equals, I'll do it in white, equals I. So I'm going to go back up here to where we found I, because it's the same I, same moment of inertia. Okay, here's the total. And then I worked out the single fraction right here. Okay. So it'd be I. And then times alpha, which I'm going to write as the second derivative of the angle with respect to time. Okay, so now I'm going to make something, I'm going to do something that is required pretty much to get the period, to treat this system as a simple harmonic oscillator, and it's to use the small angle approximation. And that says that sine of theta is approximately equal to theta. And this comes from the Taylor series expansion of sine. Doesn't really matter too much about that. The only thing that matters is that this is, approximately true, I'll say, for small theta. And in the problem statement, I believe it does say, a small angle theta. So that is assuming that we can use this angle approximation. I guess for completeness, I'm just going to write the Taylor expansion for sine of theta, which is just a way to express a function like sine, or any differentiable function you can express as a Taylor series. And it's just in terms of polynomials, so they're easier to work with. So off to the side, I'll say, so here's the Taylor series for sine. Sine of theta is So it's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on. And it continues forever. But if we truncate this just here, we get that, well, sine theta is not equal to theta. It's approximately equal to theta if theta is small. So that's why we can say sine of theta is approximate to theta. Anyway, now we can rewrite this as negative mg r. Instead of sine theta, we're going to put theta. And that's going to equal, I guess I already copied it. It's going to equal this times second derivative of theta with respect to time. Now I'm going to divide both sides by this, which means multiply by the reciprocal. So I'm going to flip the equation and write d2 theta dt squared equals, so I'm going to go like this. Negative is going to be here, and then I'm going to flip this fraction, so the 2 is going to be on top, but then we still have this on the numerator, so it's going to be 2 mgr divided by all this. So that's going to be mr squared plus little m little r squared plus 2 little m big R squared, and then times theta. Now we have that form of simple harmonic motion where we have the derivative of theta, the second derivative of theta. We have theta right here. We have a negative sign, and then we have a bunch of constants. So that means the solution to this differential equation is x of t is a cosine of omega t plus phi, where omega is defined to be the square root of this big constant that I circled in red. So that's 2 mgr divided by capital M, capital R squared plus little m little r squared plus 2 little m big R squared. Okay, now since the period, I'll write it over here, the period is 2 pi over omega, all we need to do is multiply this by 2 pi and then reciprocate the fraction inside, and that'll give us the period, because here omega is on the denominator, so we just need to flip the fraction. So I'm going to do that, and at the same time, I'm going to rewrite this numerator a little bit by grouping these two together and factoring out the r squared. So period equals 2 pi times the square root of, so we flip the fraction because omega is on the bottom. So I'm going to factor out the r squared, and when I do that, I'm left with m plus, hold on, wait. Yeah, that should be right. M plus 2m times r squared plus m r squared divided by 2 mgr. And that should be the period. Let me check. I'm going to bring this image down again. Oops. I guess the arrow is still attached. Yeah, that looks pretty good. So we have, oops, I can't get it like that. Okay, here we go. Yeah, okay, so we have m plus the 2m r squared, mr squared, 2mgr, 2 pi. I guess they have it, they have it raised to the 1/2 power, but same thing, square root 1/2 power. Oops. Okay, well, that shows that the period of the system is equal to this expression, and then the velocity of the center of mass of the, what was it? The velocity of the center of mass of the smaller disk is this expression at the moment it passes through equilibrium.